So you've already learned how to find the probability of independent events, specifically ones that occur in a row or in succession. So in order for us to make the segue into using the multiplication rule for dependent events, a new type of probability must be introduced, and that is called conditional probability. Let's start with the symbolism. If you look at this right here, you will see that there's a lot going on, right? We know we have the probability of symbolism right here, right? So the probability of. So what is this saying? It's saying the probability of event F given that event E has occurred. So this symbol, which is called a pipe on the keyboard, is also another word for given. So again, this symbolism highlighted in blue represents the probability of the event F given that the event E has occurred. Okay, so on the side here, let's talk about where we're going with this using what you've already learned, specifically the multiplication rule. You know that the probability of E and F is equal to the individual probability of E times the probability of F, specifically for independent events. This doesn't change. This is always going to be true. And the key is that whatever you did with E that occurrence would not affect the occurrence of F. And we knew that because, for instance, if you replaced the card into the deck or put the cube back in the bowl, then what ended up happening, you refreshed the deck or the bowl to its original state. So why do we need conditional probability? Well, conditional probability is here so that we can deal with dependent events. It's basically making a visual showing of the fact that the occurrence of E is actually altering the occurrence of F in some way in terms of probability. So me saying just the probability of F is basically saying there's nothing. You just find the probability of F. There's nothing affecting F to really have any consequence to it. So what's going to end up happening when we switch to dependent events, this last term, the singular probability of F, is basically going to turn into the probability of F given E. So what this is going to end up saying is that, yeah, E is affecting F, so we actually have to write it in a different way. I will explain this in the next video when we talk about multiplication rule for dependent events, but for now, it's very important that students know why we're learning about conditional probability and specifically how to calculate it. So speaking of that, how do we calculate it? Well, we have a formula. The probability of F given E will be equal to one of two different formulas. Either one will suffice. The probability of E and F over the probability of E, but also the number of outcomes in E and F over the number of outcomes in E. We will tend to use this formula more often, believe it or not, but I'm going to show you some more details with examples and stuff just to show you why we will tend to go in that direction. But first, we will use this formula just to show you why we end up with this one eventually. Okay, let's look at an example. It says, in a school of 1,000 students, 250 are seniors, 700 take math, and 180 are seniors who take math. What is the probability of randomly choosing a student who is taking math given the student chosen is a senior? When it comes to examples like this, any probability problem, you always want to look and see what they actually want from you. Here it looks like they're looking for the probability that a student is taking math given the student chosen as a senior. So right away, the thing that should pop out at you is the word given. Just like with the addition rule and the word or, conditional probability, the word given signals that that's what the direction you're going to be going. Next, we have to define our events. So it appears that in this problem, the events are being a senior and taking math. So we just want to make sure that we have our variables set up in a way that will work very nicely. So we could define, let's say, E as seniors and F as taking math. Okay, and if the goal is to find a student, probability of a student taking math, given that they're a senior, then what are we doing here? We're doing the probability of F given E. So we're going to write that out. Probability of F given E. So math given senior. Okay, so let's start with the initial formula with probabilities here. So that's going to be equal to the probability of E and F over the probability of E. Okay, so what does that look like in our problem? Well, we'll start with the probability of E, the denominator, because that's pretty more straightforward, we'll say. So what is the probability of E? Or in other words, what's the probability that they're a senior? Well, they told you that there's 250 that are seniors out of the 1,000 students. So that should be pretty straightforward. But the top piece is a joint probability that they are both math and seniors. So if you look through this, this looks like just the probability of senior. This looks like just the probability they take math, but then over here, this concept says seniors who take math. That represents the and probability, which means we're dealing with 180 over 1,000. Now, from basic math concepts of fractions, remember that if you divide by a fraction, you multiply by its reciprocal. So if you were to do that, you would end up with this as your result, and these would cancel, and you would end up with 180 over 250, which, by the way, is exactly 0.72 as your probability. Okay, so now let's see why this other formula over here works okay. So I'll write or here. Let's say we went to the number in E and F over the number in the event E. Well, if you look at the number of observations that are in the event E, well, that's the number of seniors. Well, look at that, 250, right? And if you look at the number in E and F, which is seniors who take math, hey, there's that 180 right there. So look what we end up back at. We end up back at the same answer. But why is that? Because if you go back to when you were doing some of the contingency tables, basically this is a joint probability and this is a marginal probability. And what we know about both of them is that they're always going to have the same denominator, which was the table total, by the way. Not relevant to this, but that's basically what happens, which means these numbers, these denominators are always going to be identical, which means they're always going to cancel out, leaving just the numerators. And the numerators are literally just going to be the number of observations in those events or event. On to the next example. So suppose the one card is selected at random from a full 52 card deck. Find the probability of selecting a king given that it is a face card. Okay, again, you'll notice here's your keyword, given. We want to define our events with variables. We'll say K is for king. We'll say F is for face card. So therefore, we're looking for the probability of K, king, given face card F. Skipping our probability stuff, because we know it's going to end up with just this formula, we're going to say that this is the same as the number of outcomes in the event F and K over the number of outcomes in F. One small thing note here that I didn't mention before, just remember if you're really going through the formula quickly and you're not necessarily looking back at the formula sheet, whatever the second variable is or event that's after the given symbol is always going to be the denominator one. So here you can see F is the given condition here, so that means that's going to end up being the denominator variable that we're going to be dealing with. The numerator doesn't really matter if you write F and K or K and F because they mean the same thing. Okay, so we start with the denominator where we need the number of face cards. So this is in the deck, basically. So remember, there's 3 face cards in each suit, but there's 4 suits. So 3 times 4 is going to give us a total of 12 face cards. Now up top here, we're looking for the number of outcomes in the overlap between face cards and kings. This can play a little bit of trickery with your brain, just to warn you, but I'll throw it over here as an aside. So basically, if you want the overlap of face cards and kings, we have, let's say, king, queen, jack, and all the suits, right? And yes, these would be different, king, queen, jacks, but we don't really need that for what we're doing. That would be basically the event face card, whereas the event king would just be all the kings. So if you're looking for where these overlap, right? Where do they overlap? Well, they overlap at all the kings, for which there are how many of them? There are 4. So therefore, this probability is going to be 4 out of 12, or 0.3 repeating. A third. Now, just to give you a little bit of insight into this, the truth is that this can all be done sort of in your head, mentally, without the formula. You're kind of using the formula in your head, but the reality is you can think about it logically. So, for example, if it's given that it's a face card, then all they care about in this problem is face cards. So that's going to be your denominator. You're going to be like, okay, so I need to forget the rest of the deck. I need all the face cards all in a group. So in your head, you end up with this right there, and then you put the 12 at the bottom because that's how many you have. But then it's asking, well, what's the probability out of this group that you get a king? So you're like, okay, well, there's 12 cards here, and 4 of them are kings. Well, there you go. 4 out of the 12 gives us 0.3333. So there are other ways to think about it. It's just a matter of whether you feel confident enough to do that. I find that a lot of students end up using the formula and are fine with that. But if you're good with just mentally doing it, this is a topic where you can sort of just write out what you have and you don't have to have a lot of work for it. Okay, so again, 52 card deck. What's the probability of a king, we'll call K, given that it is a heart? Okay, so that's a little different. We'll call that H. So we'll do probability of K given H. So that's going to be equal to the number of hearts and kings, the joint probability together, over the number of hearts. So remember again, whatever is in the given condition is also going to be in the denominator of our statement. Okay, so over here again, so first we want to know the number of hearts in the deck. Well, we know there's 13 cards in each suit. How about the numerator? So we're looking for when heart and king occurs at the same time. So we need to look at that and be like, okay, so if we have all the hearts, so that's going to be basically an entire suit of 13 cards. And then we have all the kings, which is going to be the 4 kings. Where's the overlap? Well, the overlap is clearly at the king of hearts, just 1 card. Therefore, the probability for this is going to be 1/13, or 0.0769. Again, though, we could have done this mentally. We could have said, given that it is a heart, so all we care about is hearts. All the other cards are thrown out. We only have 13 hearts in front of us. How many of those hearts are kings? 1 of them. So therefore, 1 out of 13. So you can see why, hopefully, doing it in your head might even be easier than trying to figure out some of this overlap stuff in the numerator. It actually can be pretty straightforward. The last concept to cover in this section is how we can find conditional probabilities in contingency tables. As you've seen before, we've had this chart on the support for whether somebody would want a special tax on junk food. And basically it was here, birth, gender, and this was stance on tax. So we had 2 variables at play in the same table. which made it a contingency table. Remember, in contingency tables, you were asked questions on both marginal and joint probabilities. Remember, marginal were around the outside, whereas joint probabilities were found from inside the table. But you were also even asked about the addition rule and how it could apply. So now we have another application, which is conditional probability. Okay, so suppose we're trying to find the probability that a randomly selected adult supports the tax given that they are female. Okay, so let's use T for tax, and we'll use F for female. It's like a true-false statement here. So we're looking for specifically for the probability that they support T, the tax, given that they are female, which is going to be equal to the number of female and supporting the tax jointly over the number of females. Okay, so let's look at the formula. So the number of females, well, they pretty much list that out for you, right? So females, number of females is right here. So that means we know that the number of females is 555. Up top, we need to know the number that are both female and support the task. Well, female and support is a joint count, which is right there, and it is 233. And it is literally as easy as that. That'll give you 0.4198 as your probability. But again, technically, you can do this mentally and not with the formula. So you can say, we know that it's given that they are female, which means what is the only thing that we care about in this study? We only care about the females. So then they said, well, out of the females, how many support the tax? Well, clearly, that's this number. So out of the females, which is 255, 233 support the tax. And guess what? That's exactly what we got when we actually utilized the formula. Another thing worth mentioning, because we're in the world of contingency tables again here. So for all of the other probabilities that you calculated, any marginal, joint, or anything with the addition rule, if you recall, the denominator was always the table total. Now take a look at this. It turns out that with conditional probabilities, it is the only probability that you're going to learn that the denominator is not the table total. The denominator instead is going to be one of these counts that are in the margins. So be very careful with that. It is common that students mess that up a little bit or confuse some of the probabilities because of the fact this is the only one that doesn't have a table total as a denominator. Okay, wrapping up with our last problem to make sure all is good. Let's find the probability that someone is male given that they're unsure about the tax. So we'll say M for male, and let's just do U for unsure about the tax. So we're looking for probability of M given unsure. So that should be the number. I'm so used to writing probability. The number of unsure and male over the number of unsure. Okay, so we're going to turn the table around a little bit here. So this time the denominator is the number of unsure people. So we immediately go, okay, last time we were in a row, now we're going to be in a column. So we only care about the people that are unsure, in which there are 27 of them. And then out of those 27 of them, we need the overlap for the top, our joint count, between unsure and male. So male and unsure lands us right here. So 5 out of 27 is going to give us approximately 0.1852 as our probability. And just like last time, hypothetically, if it's given that everybody's unsure, that means we only care about this column. Literally nothing in the rest of the chart and the table matters. So out of that column, given that they're unsure, we know there's 27 of them, and how many of those unsure people are male? 5. So we get 5 out of 27.